Welcome back, physics fans, and here we are on electrostatics, the second lesson. Well, actually, the second topic. The lesson goes a little longer than this one topic. It will be on electric fields. Now, initially, we'll start off with gravity again. We'll just come back to a quick viewpoint on what electrostatic fields are. No, gravitational fields. Gravitational fields, we have to kind of understand what a gravitational field, how it looks like, and then we'll understand it. So, when we have a large planet, it's going to have a G field around it. How do we know? Well, you place an object there, it's going to fly towards it. So if you place an object around it, it's going to have an attraction there. Before you place the object there, there was a field. There was a field at this location. There was a G field at that location. And if we place the mass there, it will get a force. So let's fill in the appropriate relationships here. The universal gravitational formula is G m1 m2 over r squared. And the definition of the gravitational field, okay, is, well, we get it from F equals mg, okay? And it becomes Gm over r squared. And this is the mass that's creating the G field. This is the mass that is creating the G field. And the gravity field as a ratio, it will be the force that the object feels and the object's mass. This is the force it will feel. Okay, and it'll feel, what is it? This is it. This is the it, this mass. So if we put this mass in this G field at that location, that'll be the force that it'll feel. And the units for gravitational field is newtons per kilogram. So without a mass in that location, all we need is one. It produces a G field, and that G field is, if we put a mass in there, it will feel a force. And that force over the mass is equivalent to that G field. Okay, so there's two ways to calculate G fields. There's the G is equal to capital G, the mass that's creating the field, over r squared. So question A, find the gravitational field strength this many meters from the Earth's center, which is about 2 million meters above the Earth. Okay, so, but we don't have to know that. It's not above the Earth that this R is. This R is to the center of that planet. So it'll be 6.67 times 10 to the negative 11th. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And the separation distance is 8.38 times 10 to the 6th squared. So it'll be Gm divided by 8.36 e to the 6 squared. And the G field will be 5.7 newtons per kilogram. Now, realistically, we have never put the direction there. We should have. It's a field. It has a vector direction towards it. So we could have always written, but we never did. But we could have always written towards the planet because that'll be the direction the force gets when you put a mass there. Part B, if what is the gravitational field strength if a 10 kilogram test mass has a weight of 75 newtons? So I have no idea where we are. We're not on Earth because we're asked to calculate G. So G is equal to F over M. And if I put in this G field space, there's a G field in it, and we get a weight of 75 newtons. If we put a 10 kilogram mass in it, this is going to give us a 7.5 newtons per kilogram G field. That's nice. It would be nice to have the direction too. Okay, towards the object that's creating the G field. If you were worried about it, you'd give a direction as towards the object that's creating the G field. Okay, that was 6 minutes and a quick review of gravitational field strength. Now notice I said a 10 kilogram test mass because we're testing out to find out what the G field is. This test mass is not creating the G field. This test mass is only to determine what that G field is. So we put this test mass in that location because there's nothing there, just a field, to calculate what that force is, to calculate what G is. Electrostatics. We define an electric field in the same manner. We say that an electric field reflects the effect a charge has on the space around it. If another charge is placed in that field, it'll experience a force. So we have a large charge here, not physically large. It could be a small little thing, but it has a large charge on it. And it has a large charge on it. It could be repelling or it could be pulling in. Because we now know in electrostatics that we have positive and negative charges, not positive and negative masses, but positive and negative. So the G field could be either direction. Sorry, E field. So if I put a little charge there, it will feel a force this way or this way. So the force of electricity is K Q Q over R squared. Now I'm going to just oh, actually, I'll leave it alone. Hang on. So the definition of an E field is KQ over R squared. Okay, and this is the little mass that we put in, but this time it's a little charge that we put into the G field, E field, sorry, to figure it out. Now, one of the things here I'm going to emphasize later in a moment that this is a scalar equation. Why scalar? Because we use a different methodology to find the direction. This is only to calculate the magnitude of the E field. This alone, we don't know what the direction is. Now, the other one that we did with gravity, we did G is equal to F over M. Remember, this was our little test mass that we put in, well, we do the same thing here. E is equal to the electrostatic force over Q. Q is the little charge that we put into the E field. It gets a force, and then that force divided by that charge will be the E field. Okay? So these are vectors, but we're not worried about them right now as vectors. We're telling you that these are only scalars for now. And the units of electric field will be newtons per coulomb. Okay, this is just reading. I want to address that right now. Sometimes I do, but then it confuses people. So, at a certain point in space, example number 4, a zero point 0.5 microcoulomb test charge experiences a force of 5.2 times 10 to the negative 4 newtons towards the south. Find the E field strength at this point. So E field can be calculated two ways. KQ over R squared, and that's what's creating the E field. That's large Q is what's creating the E field. Or we could do it by F over small q by placing a charge in that field and finding out what the force is, dividing it by that charge also gets you that E field. And that's what we're going to do here. This is going to equal the force over the charge that we're putting in, the small test charge. Usually they try to help you with the word test. As soon as it says test charge, you know you're using this formula. And that's 5.2 times 10 to the negative 4 newtons divided by 0.5 times 10 to the negative 6 coulombs. Mr. Calculator, 5.2 e to the negative 4th divided by 0.5 e to the negative 6, and we get 1,040. What are the units? Thank you, newtons per coulomb. Now, it will have a direction. We're not putting that in yet. Right now, we're just doing the scalar. This big box coming up here is going to tell us all about the rules for direction. Find the electric field strength 0.5 meters to the right of this charge. Is this a test charge? No. That's the charge, and we're trying to find the E field to it. So we have a charge, this Q, and we're 0.45 meters from it. And at this location, we want to know what the E field strength is in there. Okay, because there's an E field going through it, being produced by this Q. So the E field is KQ over R squared. And that's going to be 9 times 10 to the ninth. The charge is 2.3 times 10 to the negative 6 coulombs all over 0.45 squared. So 9 e to the ninth times 2.3 e to the negative 6 divided by 0.45 squared. Okay, so these are the scalar answers. These are not the finished answers. We've got to learn the rule on it. Okay, this is the rule. How to find the direction. How did we find the direction on Coulomb's law? KQQ over R squared. We took a look at the charges, plural, charges, and then go, okay, well, the opposites attract. So we now know the direction because if one was positive, one was negative, we could do it. Well, we now have another rule for E fields. The direction of the E field, well, with gravity, it was never an issue because gravity always attracts. But since electricity can repel or attract, we need a definition. Okay? So, in other words, we need to define this. This is not something that everyone could agree with. Kind of like, what side of the road do you drive on? As long as everyone agrees, then when we get an answer, we'll all understand. That's the whole purpose of it. Is there a right and a wrong place to drive? Well, in each country there is, but it's not really, it's just the rule of the road. So in the rule in physics, we make one rule for the whole world to understand. And then we all understand when we write a number. That's all. We just need to make a rule. So this definition, it says, we say that the direction that the E field is the direction that a small, imaginary, it actually doesn't exist, positive test charge. Okay? The key word there is positive. Okay? And the second key word is test charge. And the third is it's actually imaginary. We want to think that it's imaginary because if we put a charge in, we don't want to change the E field that's already there. So it's if we had put one there, what would happen to it? What would happen to it? That's the answer is which way would it go? Which way would it point? So let's go back up here. We have a test charge that's experiencing a force. Okay? And it's experiencing a force to the south. This force is to the south. But the force is on a negative charge. A negative charge. The definition says we have to use a positive charge. To write the direction of this E field, we have to use a positive charge there. So if we had put a positive charge there, what direction would this force be? Flipped, the other way around. That's the direction of that E field, north. Because you have to use a positive test charge, and that's the way it goes. Okay? So the E field can be in the opposite direction as the force. No duh. Whoops. And the last one. Find the direction to the right of this charge. So if we had put, I'm going to erase it. If we had put a positive charge there, which way would the E field be? Well, this is a positive test charge. So if this is positive and we put a positive there, it would go to the right. right, we're going to stop it here and continue on with the next lesson. Thanks for watching. Subscribe. Leave the comments there so my algorithm gets up there, so I get like 100 million views today, and I could beat Mr. Beast. Thanks. Bye.